All right, here we go. 7.3 independent and dependent events. I'm going to try and make this nice and fast. Go ahead and copy down independent events. If the occurrence of one event doesn't affect the other, then your two events are what we call independent. And then to find the probability of independent events, we have right here, if A and B are independent, then P of A and B, so the probability of both of these events happening, is just the probability of A times the probability of B. My finger is very dirty. It's from the marker. Okay. All right, so, think about this before we start these problems. I mean, go ahead and write this down. But we're going to find, in this first example, the probability of getting a 6 and then a 4 on what we call a number cube, otherwise known as a dice. So, dice has 6 sides, which it's actually probably pretty helpful to say that our n value is 6, the total number of possibilities or outcomes. Well, what's the probability of getting a 6 on a dice? Well, there's only one 6, and there's 6 sides, so the probability of getting a 6 is 1/6. But think about getting a 4 after rolling a 6. Does getting a 6 affect getting a 4? No. If you roll a 6... Oh, I was hoping to roll a 6 there. And then you roll a 4. Let's see if I get it. Oh, dang it. Well, did the first roll affect the second one? No, it didn't. So when I go to find the probability of getting a 4, there's only one 4, and there's 6 sides. So the probability of getting a 4 is also 1/6. So for 6, it's 1/6. For 4, it's 1/6. By that the formula you just saw, we just take these two probabilities and multiply them. 1 times 1 is 1. 6 times 6 is 36. And that's your probability of getting a 6 and then a 4. Here's another example. Tossing heads, then tails, then heads. Then tails, then heads when tossing a coin 4 times. I mean, think about it. If you flip a coin, you get heads. Ooh, let's see if I can get it. And then tails. Ooh, on a roll. Then tails, come on. Oh, God, didn't make it. And I dropped the coin. But anyways, whatever you get here on the first trial doesn't affect what you get over here. And you probably know that, but it's just something you got to think about when you're going through these problems, because in some problems, the outcome of one does affect the other. Now, let's go ahead and just do this problem real quick. We want to find the probability of tossing heads, then tails, then heads when tossing a coin 4 times. So that means we're going to have 4 different fractions. You don't have to draw the blanks like I just did. Just a little visual. You don't have to do that, though. So what's the probability of tossing heads? Well, there's 2 outcomes. There's only one side that has heads, so it's 1/2. Tails also has 1/2. Tails, again, 1/2. Then heads is 1/2. The formula says to just multiply these. 1 times 1 times 1 times 1 is 1. 2 times 2 times 2 times 2, that ends up being 16. So the probability of you tossing heads and tails and tails and heads is 1/16. Independent events are pretty easy. Then you get to dependent events, where you usually have to think a little bit more about what's going on. Dependent events is where the occurrence of one event influences another event. And then this involves what's called conditional probability. It has some new notation here. It's that bar right here. The way you read this bar is the probability of B given A. Sorry, I should have written that. So the way you say the inside of this is, really the whole thing. The P stands for probability of. And then the inside is B. That line is given A. So B given A. And what that means is finding the probability of B given that A has already occurred. And I underlined, probability of B in blue and A has already occurred in purple. You don't have to do that, but it's so key. So what this means is probability of B can only occur if A has occurred. And the reason why we do that is this formula right here. The probability of dependent events is given by this formula. P of A and B is equal to the probability of A, So whatever that first probability is, times the probability of B given A. So I'll show you an example of what this looks like. All right. This is our last problem on here, by the way. I kept it short. Okay, so you have a basket that contains 5 apples and 7 peaches. You randomly select one fruit and eat it. Then you randomly select and eat another piece. Find the probability that the first fruit was an apple and the second was a peach. So if you think about this, you have your basket has how many total pieces of fruit? Let's actually establish that right now, that your total number is 12. So you have 12 pieces of fruit. Now you randomly select one and eat it. And let's just go by the problem. It says find the probability that the first fruit was an apple. How many apples are there? There's 5. So our first probability is 5 over 12. And that correlates, I'm just going to put this here real quick. This is the last paper that we just looked at. This 5/12 correlates to this probability, because that's the first thing you were trying to find. I guess you could say, if you wanted to, is in this problem, capital A stands for the event apple. And the other event is peach. Because that's what we're trying to find right here. Apple and peach. Apple first, then peach. So probability of apple is 5/12. Then the second part of the formula has us find the probability of B given that A has already occurred. And so we're assuming that this has already happened, this 5/12 probability. Now, if you think about it, if you've taken that one fruit out, you're down to how many fruits total? Your new n is now 11. So when I go to put my second fraction here, I'm not going to put 12 because I've already had a fruit. You're down to 11. Now, you just got to think here, if we took one apple out, did that change how many peaches are still in the basket? No. So there's still 7 peaches in here, which means that we'll put 7 on top. We're going to go ahead and multiply this. 5 times 7 is 35. 12 times 11 is 132. It turns out that this does not reduce, so that's your probability. Let's actually think one more thing before we end here, and this is important. What if I want you to find the probability of apple and then apple? What's the probability that your first fruit was an apple and your second fruit was an apple? Well, your first probability will still be 5/12. But assume that the first fruit you took out was an apple. How many do you have total in the basket left? You're down to 11, just like before. But if you had 5 apples to start and you took one out, how many apples are you down to on your second selection? You're down to 4. And so that's how it would change if you were doing apple and then apple again, instead of apple and peach like our original problem here. Then you would just multiply and simplify. I'm not going to do that because you guys know how to do that. All right, and that's independent and dependent events. You will have a quiz. In fact, let's go ahead and just make it so that you see that. We're going to have a quiz on 7.1 to 7.3, the class after you do the 7.3 practice. So when we go to do 7.4 practice, we'll have a quiz that same day. It'll be a short quiz, but just be ready with your notes. A couple more things, because I get hounded for requests for shout-outs. Okay, here we go. All right, so new section, new us. You know who I'm talking about. Period 3, wanted me to shout them out, especially Tommy Longhair. And then there's Dina, a.k.a. I don't want to say this, D-Nasty. And shout out to Chris Taylor, making names out here. Download his mixtape on SoundCloud. He's the greatest of all time. You can also call him Young Fresh Boy with the heater, gratata. I feel so lame saying all that. And here's your math joke. You have to be odd to be number 1. Thank you.